Today we are going to see the design of piston. Here photograph of the piston is shown. Its different parts are, so this is the top line, this is ring section, and below the ring section is skirt. Here hole is seen, so in that hole piston pin is fixed. In the next photograph, piston head or piston crown is visible. Here are the two piston rings. One is the compression ring, another one is oil ring, and the last photograph is piston pin. 2D sketch of the piston is shown here. The top portion is top land, then ring section, then is skirt. D is diameter of piston. Here are 4 rings. So first 3 rings are compression rings, last ring is oil ring. Then the pin is fixed in the piston boss. Then piston pin is there, which is shown here. So main parts of the piston are piston head, piston ring, skirt, and piston pin. So let's see the design of piston head. The Greshoff's formula for finding the piston head thickness is shown here. It is Tp equal to square root of 3 P max into D square divided by 16 Ft. Tp is the piston head thickness in centimeter, D is diameter of cylinder in centimeter, P max is maximum gas pressure, Ft is the allowable bending stress in kg per centimeter square. For the aluminum alloy, the value of Ft is 600 kg per centimeter square. P max is previously calculated. P max is 52.5. So it depends upon BMEP. So it is 9 to 10 times BMEP. We can find out BMEP, that is brake mean effective pressure, by using the formula, that is BMEP divided by IMEP. IMEP is the indicated mean effective pressure equal to mechanical efficiency, or the mechanical efficiency is the ratio of BMEP to IMEP. So if the values are substituted over here, it will give Tp as 1.28 centimeter, that means 12.8 millimeter. Similarly, the empirical equation to find Tp is Tp equal to 0.03 D plus 1.5. D is diameter of cylinder, this is 10 centimeter. By substituting the value of D, the Tp will be 1.8 centimeter, that is 18 millimeter. So Tp, that is the thickness of piston head, is 18 millimeter by second equation. Then third criteria for Tp is based upon the diesel engine or the petrol engine. For 4-stroke diesel engine, if the material of the piston is aluminum alloy, then piston head thickness is 0.13 D to 0.16 D. If this is CI, cast iron, then piston head thickness is 0.11 D to 0.13 D. And for 4-stroke petrol engine, if material is CI, piston head thickness is 0.12 D to 0.14 D. Here for present case, Engine is diesel engine, it is 4-stroke, and metal of piston is aluminum alloy. So value of TP is 0.13, D to 0.160. Substituting value of D, TP is 13 millimeter to 16 millimeter. So fourth consideration for finding the value of TP is based upon heat dissipation. The formula is like TP equal to H divided by 12.56 K TC minus TE. H is heat flow rate through piston head, it is in kilocalorie per hour. K is constant. TC is combustion chamber temperature in degree Celsius, and TE is piston edge temperature in degree Celsius. H is heat flow through the head is calculated by the formula, that is H equal to CW into HCV into BHP. C is constant and it is 0.05. W is specific fuel consumption, it is in kg per bhp per hour. So for diesel engine, we are considering value of W as 0.2 kg per bhp per hour, and this HCV is higher calorific value. So this higher calorific value is for diesel engine 10500 kilocalorie per kg, and BHP is brake horsepower. Here we are considering 3 cylinders, so BHP per cylinder will be total BHP divided by number of cylinders. Total BHP is here 35, so BHP per cylinder will be 35 divided by 3, value is coming 11.67. Substituting value of CW, HCV and BHP, H will be equal to 1225.35 kilocalorie per hour. K is coefficient depending upon material. For aluminum alloy, the value is taken as 1.5. As I told, TC is combustion chamber temperature and T is piston edge temperature. The difference is lead. The difference is 75 degrees Celsius for aluminum alloy. Substituting the values of H, K and TC minus TE, it will lead to the value of TP as 0.86 centimeter, that is 8.6 millimeter. So by using different criteria, the values are like 12.8 millimeter, then 18 millimeter, then 13 to 16 millimeter, and here with heat dissipation criteria is 8.6 millimeter. So maximum value is coming in the empirical equation, that is 18 millimeter. So let the TP, and that is the top line or the thickness of piston head, as 18 millimeter. Then ribs are provided to make piston head rigid and carry the thermal load. Let's consider here there are 4 ribs. Thickness of rib is given as 1.3 to 1.2 into TP. So this 1.3 into 18, TP is 18 to 1.2 into 18, so it is coming to be 6 to 9 millimeter. So thickness of rib is considered as 7.5 millimeter. Then piston rings, there are two types of rings. One is compression, another one is oil ring. Two dimensions of ring we are going to find basically. One is BR, another one is TA. BR is the radial thickness and TA is axial thickness. Radial thickness is given by the formula. So this is also the Grashoff's formula. Radial thickness BR equal to T square root of 3 PW divided by FT. BR is radial thickness in centimeter. D is diameter of piston. PW is the wall pressure in kg per centimeter square. It is considered here for the present case as 0.35 kg per centimeter square. FT is permissible stress. This is taken as 1000 to 1500 kg per centimeter square for cast iron rings. Let that value is, FT value is 1250 kg per centimeter square. Substituting the values, the radial thickness is 0.29 centimeter, that is 3 millimeter. In the figure, radial thickness is shown as BR and axial thickness is shown as TA. First is compression ring, another one is oil ring. Oil ring has the holes for the passage of oil, and there is the difference between there is gap between the piston edge, the piston ends. So there is gap between the compression ring ends. So that gap is called as piston ring gap. Then this axial thickness TA is given as D divided by 100 into NR. NR are the number of rings, D is diameter of piston. Substituting, this is 10 centimeter, 10 into 4, 4 are the number of rings. TA is 0.25 centimeter, that is 2.5 millimeter. So axial thickness of ring is coming as 2.5 millimeter. Axial width, so it is also called as axial width TA. This can be calculated by the empirical equation TA equal to 0.721 of BR. The value of BR is 3, so 0.7 into 3 2.1 and 1 into 3 is 3, so it is 2.1 to 3 millimeter. So it is considered as 2.5 millimeter. Therefore section of ring is 3 millimeter is a radial thickness and axial thickness is 2.5 millimeter. So thickness is rectangular thickness is like 3 millimeter by 2.5 millimeter. Then this is the width of top line. Width of top line is given as 1 TP to 1.25 TP. So TP is 18, so it is 18 to 21.6 millimeter. It is considered as 20 millimeter. Width of other ring lands. Sometimes some extra piston rings are provided, so that is just below the top line, or the rings are also some rings are also provided at skirt position. So that ring width is given as 0.75 TA to 1 TA. TA is axial thickness. Axial thickness is here 2.5. So 0.75 into 2.5 to 2.5. It is coming 1.9 to 2.5 millimeter. So let's take as 2.2 millimeter. Gap between free ring ends. So is also called as piston ring gap. It is 3.5 BR to 4 BR. It is 3.5 into 3 to 4 into 3. It will be 10.5 to 12 millimeter. So it will be like 11 millimeter is the gap. Gap when a ring is in the cylinder. Sometimes rings are provided inserted in the cylinder. At that time the gap is given as G equal to 0.002D to 0.004D. D is in millimeter. It is 0.002 into 100. This is in millimeter. Okay. So 0.002 into 100 to 0.004 into 100 is coming 0.2 to 0.4 millimeter. So let's take this as 0.3 millimeter. The next is piston barrel. Thickness of piston barrel at top is given as T1. Empirical relation is T1 equal to B plus 0.03D plus 4.5. B is calculated as BR plus 0.4. BR is, it is 3. It is the axial thickness 3 plus 0.4. So it is radial thickness. Radial thickness 3 plus 0.4. It is coming as 3.4. T1 will be like 3.4 plus 0.03 into 100 plus 4.5. It is coming as 10.9 millimeter. So let's take T1 as 11 millimeter. Thickness of barrel at open end is calculated by T2 equal to 0.25 T1 plus 0.35 T1. T1 is thickness of barrel at top. Substitute value of T1, it will give value of T2 as 3.2 millimeter. So these are at the top thickness is 11 millimeter and at bottom thickness is 3.2 millimeter. Right. Then next, the skirt length is shown here. It is from the point where the piston ring ends to the end point. So it is calculated on the basis of maximum gas load. The maximum gas load equal to pi by 4 into d square into P max. This maximum gas pressure, this cross section area pi by 4 into d square, it is coming 4,123.3 kg force. Side thrust in the liner, so it is coming on the skirt. So that side thrust value is taken as R equal to 0.03 to 0.1 F. F is maximum gas load. So let's take R equal to 0.1 F. It is coming 412.33 kg. Now R is calculated as L into D into PB. L is the skirt length, D is diameter of piston, and PB is bearing pressure. It is taken as 4.5 kg per centimeter square. Substituting the values, it will give the length of skirt, and it is coming 9.5 centimeter. Next part is piston pin or wrist pin. Piston pin is used to connect piston with the connecting rod. There are three types of piston pins: full floating, semi floating and fixed. Full floating pin is free in both piston boss and small end bush of the connecting rod. Pin is secured by using circlips against end moments. Semi floating pin is free to move either in piston boss and clamped in small end of the connecting rod and vice versa. If pin is free in small end of the connecting rod, then it will be clamped in the piston boss. Third type is fixed. The piston pin is fixed at both the points, that is at piston boss and at small end of the connecting rod. Design of piston pin. The maximum gas load is calculated as F equal to L1 D into PB. F is maximum gas load. that is pi by 4 into d square into p max. This previously calculated is 4123.3 kg. Length, this L1 is length of pin in bearing, this 0.45 into d, 0.45 into 10 is 4.5 centimeter. Diameter of d is diameter of piston pin. Pb is bearing pressure in kg per centimeter square. Its value is taken as 250 kg per centimeter square. Substituting the values of different parameters, diameter of piston pin is 3.67 centimeter, and that is 3.7 centimeter. Now the piston pin is to be checked for bending failure. It is subjected to bending. Maximum gas load is F. Let the maximum gas load is acting at center. So that F is the reaction at both ends will be F by 2, and bending moment can be calculated for this as F into d by 8. F is maximum gas load, d is diameter of piston. Substituting the values, M is 5154 kg centimeter. Then bending stress Fb equal to M by Z. M is bending moment, Z is modulus of section. For circular section, modulus of section Z equal to pi by 32 into d cube. So this M will be equal to Fb into Z. Z is pi by 32 d cube. So M is pi by 32 d cube into Fb. Fb will be equal to M divided by pi by 32 into d cube. Just putting the values of M and d cube. The induced value of Fb will be 1036 kg per centimeter square, whereas the allowable Fb is 1400 kg per centimeter square. So induced Fb, or actually acting Fb, is less than the allowable Fb. So piston pin of diameter 3.7 centimeter is safe in bending if pin is solid. However, if pin is hollow, let diameter, outer diameter is 3.7 centimeter, inner diameter is 2 centimeter. M will be pi by 32 do raised to 4 minus di raised to 4 divided by do into Fb. Substituting the values, Fb will be 1133 kg per centimeter square. That is induced value of bending stress Fb is less than the allowable value of bending stress. So design is safe in bending for both. That is, if we consider piston pin as solid and if you consider piston pin as hollow. For solid piston pin, diameter is 3.7, and for hollow piston pin, diameter is 3.7 OD, outer diameter, and inner diameter is 2 centimeter, and 3.7 centimeter and 2 centimeter. So with this, the design of piston is completed. Thank you.